confirm that we all have a good graph before we continue in calculating some probabilities. So problem tells us that we have a bus that comes every 30 minutes, but it could be up to 20 minutes late with a uniform distribution. So that means that we have a bus that could be up to 20 minutes late. So follows a uniform distribution, so it should look something like that. Now, how you label your bottom, that's up to you. You can just count by 5. You don't have to fill up the whole thing. However, you do need to make sure in this case that it is on the y-axis because we are anywhere from 0 to 20 minutes late. Yes, sir? No. Bring it out on the back. Now, of course, we need to determine how high our graph is going up. So we can use our area calculation to do that. What is the area of this beautiful rectangle? Yes. How wide is this rectangle? 120. Which means that we have 120. Good. Questions on that? All right, so what is number 1 asking for? The bus will be no longer than 5 minutes. Okay, no more than 5 minutes late. How do we write that in a column? So less than equal to 5. Right. So we're looking at this space right here. How wide is it? We were already talking about that. What's our height? 20th. So we get. Let's say 25% chance that they are no more than 5% late. All right, take 3 minutes. Try 2. Try 3. See if you can get those worked out. So number 2 asks us about at least 15 minutes. Of course, at least means greater than or equal to 15. So I go over here to my 15 spot. Fill in that rectangle. I put in a long time. How wide is that rectangle? 5 minutes. So at 5, I still have a height of 1/20th. So we have 1/4. Which should make sense because, you're looking at 5-minute intervals. Of course, all of them are going to have the same probability because they all have the same height. So any 5-minute interval, even if you went from, 8 to 13, would still have a probability of 1/4. Okay. Questions about yes, ma'am. Do you have a wire? I do. I don't know. Sorry?
Like this attract something from like every possibility.
I'm not sure I understand what you're talking about.
He doesn't limit the quality, they do increase the attract
With? Yeah. All right, number 3 says, what is the probability of the bus will be between 8 and 12 minutes? So that would be 8 to 12. Everything will be so far. How wide are we from 8 to 12? Or was our height still the same? Yeah. What do we get? So are we not counting something? Width from 8 to 12, so we're 8 to 10 is 2, 10 to 12 is 2 more. It's 4. Again, we're counting the space, not the number of numbers. Other questions? I know that some of you have confusions. Some of you are just talking. All right, so take a couple minutes, see what you can do with the middle one. So in this particular case, they're talking about the elevator. Of course, you shouldn't have to wait 12 minutes, but if the elevator happens to be on floor 9 when you press the button and it's heading down and has to stop between every floor between there and back up, it could take 12 minutes to get there. So we are looking at an elevator that could be anywhere between 0 and 12 minutes late. So I don't know, let's go 3, 6, 9, 12. That's fine. That's fine. However you want. So we have our little rectangle set up now. What is our height going to be for our rectangle? 12. So we are 12 wide on our graph. Kiana, do you understand why it's 1 over 12?
No.
Okay, because our rectangle itself goes from 0 to 12. So it's 12 spaces wide. Other questions? All right, so 4 says find the probability that someone waits less than 2 minutes. So less than 2 minutes, obviously I'm going to go with 2 here, so somewhere in that region. How wide are we from 0 to 2? Of course, our height is 12. So we end up with 1/6, which would be about 17%. 0.166666667. What did you do? Folks, you should be talking. I need to be able to hear you. 10 times 1 out of 12. Well, it's not 10 wide, 2 or less.
No, because remember I asked you to subtract and get the big.
Right, so 2 minus 0 is 2.
Oh, really?
Yes.
Wait, what did you subtract? I subtracted 12 minus 2.
Well, it's not going up to 12. It's going from 0 to 2. So 2 minus 0 is 2. Any other questions? All right, number 5 is find the probability that someone waits more than 5 minutes. All right, so 5 will be somewhere in here. How wide are we from 5 till the end of our rectangle? 7 long. Times, of course, our height. So we end up with 7/12, so you can't simplify that. Maybe about 0.58-ish, 58%. Look at it as a decimal. Questions? All right, so you notice in the last scenario, we're talking about some temperature variations. So it doesn't have to be time that we deal with. Notice that this temperature ranges from 65 to 90, so make sure you start that graph appropriately. Make sure you figure out your width appropriately so that you can determine your height. I'll give you a couple minutes to try it out. Oh, it's because it's part of, like the other ones did. All right, so in this case, we're starting at 65. So we go from 65 to 90, so we don't want to be touching our y-axis. That's the first thing you want to check for. It should be a freestanding rectangle. Wait, why is your rectangle? 65 to 90 is what told us the temperature range. So how wide is that rectangle? 25. So that means our height is 125. Questions about setting up the graph? The graph is from 65 to 90. So we move on to number 6. Find the probability the temperature was less than 70. So that, of course, would be from here over to 65. How wide are we? 5. And our height, of course, 1/25. So we have about a 20% chance.
I don't want forms.
J5, that's 1/25. Divided correctly. Other questions on number 6? Seven. We want at least 70. But of course, 70 or more, which is the rest of our graph, honestly. So you can do this actually one of 2 ways. You can obviously look at it as we have been doing and say, okay, that's 20 wide times 1/25. That gives me 4 out of 5. Or you can say, hey, look, this is the other half of my total graph. So if I do 1 minus my 1/5, it gives me my 4/5, because that's essentially the complement of what we did in number 6.
Okay, so you didn't put 20 over 25, you just,
So we did right here.
Yeah, I got 8, 10.
okay.
Ooh. You take 20, well, 8 tenths, so you need to still simplify that.
Oh.
Any other questions? Alright, so let's head back to our reading guide, where we have the rest of the answers about the normal curve finished up. Number 9 asks us, what is another way that you could describe the normal curve? Well, what does that look like? Bell-shaped. So in order for something to be a normal situation, it has to be bell-shaped. Of course, keep in mind that when you have something that's bell-shaped, your mean, your median, and your mode should be fairly similar there at the center. So those are going to be very important as we move through our discussions. The next question asks us about something called the inflection points. On these normal curves, you have some interesting things that happen. You see in the middle, of course, we have this hill that occurs. And if you think about, our old friend parabolas, on this hill, the parabola would come down like that. But you'll notice that at these things called the inflection points, that curve changes. And so really over here, you now have a parabola. It's going up like this. And then over here, you hit that spot, and you have a parabola coming down like that. It would be a lot easier to finish this up if you stopped talking. And so at those inflection points, you have this curve changing that happens. It goes from being an upward to a downward, and then back to an upward. Those are important because it divides up the curve. So of course, we said we have our mean and our median and our mode at the center. Once you move out away from that center and you get to that inflection point, that's actually where the standard deviation shows up. So if you have a mean of 10, let's say standard deviation of 3, that means if we add on 3 to this 10, that means that 13 is going to be right here at that first inflection point to the right. If we subtract off 3, that of course gives us 7, which means the inflection point from the front of the graph is happening at 7. And so that helps you divide up your graph, which will be important as we continue our discussions of the normal curve. Denise, what was your question? Parabola, that's what you get when you graph a quadratic equation. They look like that. Now, of course, this means that the mean and the standard deviation are extremely important to the normal curve because the mean obviously tells you where the center is going to be. The standard deviation gives you some information about how spread out the graph is going to be. And so the question, of course, becomes what happens when you change a mean or you change a standard deviation. So number 11 asks about what happens when you change a mean. Keep in mind that we are drawing this on a coordinate plane. So right here we have our y-axis and our x-axis that are going through. And so obviously, if our mean is 0, we have a normal curve that's centered on the y-axis. If, however, our mean changes and shifts to 3, that means our curve is going to move over 3 spots. So the mean basically tells you where that graph is going to be centered along our x-axis. Questions about that? Stop talking. Stop talking. Which questions?
Okay, you said,
Stop talking.
you said the mean centers off where the graph is.
Mm-hmm.
So why isn't the first one centered off?
Because its mean is 0, so it has to be on the y-axis. Now, the standard deviation, of course, tells us how spread out our data is. So the standard deviation is also going to tell us how spread out our graph is. You'll notice in the pink guy right here, we have a standard deviation of 1. Blue guy has a standard deviation of 2. So as you increase your standard deviation, obviously those inflection points get further away from the mean. So it actually spreads out the graph. So essentially, the larger your standard deviation, the wider your graph is going to be. Obviously, if it starts to spread out, then it's going to have to get shorter because you have to maintain that probability total of 1 underneath the curve. So the smaller the standard deviation, taller and skinnier, the larger the standard deviation, shorter and fatter your normal curve is going to be. Questions about that? Yes?
Okay, so how does the mean play into
The mean does not play into the standard deviation at all. So you see that the mean in both of these has a mean of 0. So it's still at the same spot. Any other question? Next question asks about properties of the normal curve. I asked that you write down the 3 that you thought seemed to be the most important. There are 7 total properties that you can see listed here. The ones that I think are the most important, or the most helpful, first of all, is the fact that it's symmetric. Because it is bell-shaped, at that middle mean point, I'm stopping right now for that. And so it's going to be the same on both sides. And that can be very helpful when you're using it to calculate probabilities, because you're going to have the same thing happening on the left as you have happening on the right, and that is very helpful. The mean divides it in half. That can also be very helpful. So you know that you have 50% of your probability on the left, 50% on the right. You can use that to help you out in a lot of situations. Finally, the graph approaches 0, but it never actually reaches it. Okay, remember we said that it can't dip below the x-axis, obviously, because you can't have negative probabilities. And in this case, with the normal curve, it never actually gets to 0. So no matter how far out you go, there's still some teensy, tiny little bit of probability out there. Super small, but itty bitty. And so essentially, the x-axis, y equals 0, is an asymptote for the normal curve. Now, 7 mentions the empirical rule. You might recall we talked about the empirical rule a couple of chapters ago, which describes how the graph is divided up based on standard deviations. And we just mentioned, of course, how the standard deviation divides up your graph into those important locations, and that actually applies to the different probabilities that are available. So this is just a reminder of what the empirical rule tells us. So if we have our mean at the center, you know, of course, 50% is this way, 50% is to the left. Within that one standard deviation, so once you hit that first inflection point on either side, you have covered 68% of your area. So 34% and 34% on each side of the mean. Once you get out to 2 standard deviations away, you've covered 95% of your area. So almost 95%, almost all of your probability will be within 2 standard deviations of the mean. Once you get out to 3, you're up over 99%, which means, as question 15 asks, how much is left for the remainder of your tail space over there to the left and to the right? It's only 0.3%, so extremely tiny. But there still is a little bit out there.
We'll never reach out.
Correct. Questions about the empirical rule? Okay. Yes?
Is it the same with, if we say something like 65 and 90?
I'm not sure I understand what you're asking.
Like, now it's 99.7, it's like on the old outskirts of the...
Right, so there is half of that on this side and half of that on this side.
So if it's like 95, I feel like kind of like close to each other, that change, I feel like it's 16.
Number 16 asks for the formula for the normal curve, and it looks like that. Please keep in mind that this fraction up here is actually the exponent on the e. Okay? So you have e raised to this business, and then you have the square root of 2 pi in the denominator there. The formula is something that happens frequently, but not used in this form. Now, of course, there should be some other familiar things there. We have mu, which of course is our population mean. We have sigma, in this case sigma squared, which is representative of our variance. And then, of course, x, which is, obviously the number that we're talking about in the question. E is your natural number. It's another irrational number like pi, which is 2.7 something. We had it in the Poisson as well. The final question that you had on the reading guide, what are the 2 ways to interpret the area? We've done all of these calculations with the uniform distribution earlier, and they were asking questions about probability. So obviously one of the ways you can interpret these things is probability. But you can also interpret it using proportion. So you can use any of these answers that we get to talk about the proportion of things that are going to follow that particular characteristic. But you also can talk about it as being the probability that that particular characteristic is going to exist. So that is an important distinction to make. And so if you're asked to make interpretations, you're basically writing sentences, one talking about the proportion, one talking about the probability. And that's how that works out. This is for March, right?